So what I'm going to talk about today is how to detect silent failure. But before we delve into that, let me do a quick intro. So I'm Wojtek, one of the co-founders of NannyML. We are a very small VC-funded startup that deals with AI monitoring. So what we try to do is basically answer the question that is asked here. We're trying to detect silent machine learning failure and then address it in some way, which seems to be quite relevant to basically almost every data scientist that right now works in models that make it to production, because models tend to fail a bit. And why do I have something to say about it that might be interesting? So I used to run a machine learning consultancy. We did end-to-end projects. And then at the end, clients were always asking us, okay, now what? How do we make sure that this thing still keeps on working? And we didn't really have an answer for that. So we started kind of investigating what happens with machine learning after it has been deployed, and if it fails, what can we do about it? Also, just before we delve into it, let me say we are hiring. So if you'd like to work in a very cool, nice, remote, high growth startup, working on core product, working on basically machine learning for machine learning, you are most welcome to apply. I'll do a bit of, I'll talk about it a bit more later on. So let's talk about how to detect silent machine learning failures in production. So what's on the plate today? First, we'll just do a quick definition of what is model failure. Then we'll, so basically just, what it is. Then we'll explain what happens when the models fail, what are the consequences of model failure, and why this is an important thing to tackle both from technical and business standpoint. Then we'll talk about the causes, the reasons why machine learning can fail and probably will fail in production. We're going to follow up with detecting machine learning failures, so really the tool set for that, the machine learning monitoring part. And then we're going to have a very quick engineering slide about how to incorporate machine learning monitoring tool set, either one you build or one that you decide to purchase, into your infrastructure. So let's start with a running example that I'll be using throughout the presentation to make the machine learning monitoring a bit more real, a bit more grounded. So imagine that you're a data scientist at a big bank having 30 million clients, and the biggest product line is long-term loans, maybe mortgage loans. And working on the core machine learning model that basically does credit default prediction. So we take the credit scores and the customer information, and based on that, we try to predict whether somebody's going to default or not. And that way we can approve or disapprove a loan. We're going to define the loan default as non-payment with 1 year. So it's not known immediately. We need to still wait 1 year to really see whether this person is going to default or not. We need to optimize for some kind of business metric. Let's pick something that's typical in fintech and banking. So we'll try to just predict, optimize for ROI, return on investment, and we're going to adjust it by some risk factors. So the more risky loans will have lower ROI, even though expected ROI might be higher. And of course, when we have a business metric, we want to approximate to using some kind of technical metric. The one that's widely used everywhere in data science would be an beta score. And in case you forgot what it is, here's just a very quick overview and an equation. Basically, what it does is we try to weigh the true positives and true negatives in a way that really reflects the business problem. So let's say that people that apply for a loan and then default are more problematic than people who would not have defaulted, but we still reject them. So we need to weigh it in some way. So imagine now we have this model. This model is bringing a few billion a year, but if the quality of the model decreases by even a few percentage points, we go from making billions to actually losing billions, and the company might go bankrupt. This is actually not an exaggeration. That's how loan applications work on big scale. And if you systematically underestimate the risk, the bank might go bankrupt. This is exactly what happened in 2008. So we have our example. Now let's talk about machine learning failure. So machine learning failure can be characterized by three things. The silent one. First of all, everything looks okay. The machine learning system still outputs predictions. It's not an obvious failure. You've seen no errors. Predictions are made if you look at them, and if you have a business person look at them, look at 50, 100, 200 examples, they will all look reasonable. The loans that should be rejected will be rejected. The ones that are kind of on the verge will be on the verge. And everything looks fine at first glance and second glance. And you don't really know whether performance is good or not, because you will see, using our example, only the real label or real ground truth a year from now. But if model fails, the performance will have degraded significantly, which is, of course, a big problem. So why is it a big problem? Let's talk about the consequences. First of all, in basically best case scenario, you will see a significant decrease in ROI, because maybe you're pricing your loans too high, you're maybe rejecting too many people. And that's still kind of good failure, because you're just losing money, a bit of money. But it might get worse in a sense that you're not only not making any money with your machine learning model, which is in the end the goal of all machine learning models, or almost all machine learning models, but also you might start losing money. You will have unforeseen and hidden risks. Here, using our example again, you can have systemic risk if model for some reason always approves some loans that shouldn't have been approved, and it does it in a systematic way. The company is almost guaranteed to go bankrupt when these people start defaulting a few years down the line, all at once in very correlated fashion. And that's not it. That's not the end of it. We can also have problems with the downstream failures. So imagine that marketing and customer acquisition department also tries to get the clients that give the highest ROI. And the highest ROI at first glance would be the people that you approve for risky loans. But if this risk is not taken fully into account, your marketing and customer acquisition channels will go for the people that should not be given the loans at all, and it will only make the problem worse and worse. So the consequences can be serious, but now let's look at the reasons behind it before we start talking about the solutions. So the basic reason is really, really trivial. As your models are trained on static data, normally, unless you use online learning, which is right now still very rare in business. So you train the model on training data set, you test it, you validate it, blah, blah, blah. It works good, ready to be deployed, you deploy it. But as time passes, the environment changes. So the input data and the patterns between the inputs and the outputs, of course, will also change. And that means that your model is no longer a good representation of the reality. So it will stop working and fail silently. Here, to have a very specific example, let's assume that the model has been trained on all population, but now more and more young people apply because maybe the bank created new, really nice, sleek web app or mobile app, and people actually start using this bank. And young people tend to be more risk prone, but the model didn't know that, we didn't model it, because there was just not enough young people to take that into account. So machine learning model will systematically underestimate risk, and that is basically a recipe for disaster. This is the kind of basic failure mode. That is the main and kind of idea why models fail in production, because things change. Now let's look at the less obvious things. One of them is that every machine learning model, as it interacts with the environment, as it interacts with the population, actually also affects the population, and the population will affect the data that the model ingests. Imagine here that the customers consciously change what they actually say in their loan application, what things they hide, because the model needs to be fully, can be fully explained, as this is the regulatory necessity. So customers will start trying to fool the machine learning system, and in time they will succeed, which might decrease the performance of the model. Another thing kind of obvious is that we can have stochastic shocks, things just coming from the outside that change how customers behave, how loan application process looks like. We can have a new regulation that imposes lower down payments, so people are more encouraged to take loans, and the system was not trained on that population. Our model is not used to that, so it will not take it into account. And the last thing is that imagine we expand even from Berlin to Bavaria, we'll have kind of different population there, different risk profiles, people will behave slightly differently, and the model again is not used to that. And then let's talk about last two reasons. One of them is very long cycles that we haven't captured in our data. One example here would be the the boom and bust cycle, which can span 20, 30, 40 years even. And if we take 5, 10 years, which is normal, to use the data from 5 to 10 years from now, we will not be able to capture this cyclical nature. And as we enter new phase in the cycle, the model will not be able to really capture the patterns that happen during this part of the cycle. And the last thing, kind of obviously, is that as our data become more noisy, because maybe there's new bugs in the credit scoring system, we'll lose performance. But that's kind of a given. So we have the reasons. We know what happens, we know the consequences, and we know the reasons. Now let's really talk about the most important thing here, which is the tool set of how to actually detect it. So detection of machine learning failure is hard because it's silent, right? And there are some ways to try to approximate it, try to find the potential secondary causes of machine learning failure or secondary symptoms. And one of them is data drift. Data drift is basically change in the data input. So not the data outputs, not what we try to predict, but just change in the distribution of data inputs. If we look at 2D example that I've shown here, we see that the data points were kind of clustered together, and still the model managed to find a very nice decision boundary between them. But as time passes, maybe they will really become bimodal. And right now you would see that the decision boundary in the second image doesn't really reflect how the model would create it again if it was retrained on the new data. And it's easy to spot it, it's easy to do it manually to make sure that there's a problem. But what if you need to work with hundreds or even thousands of features? Then, of course, this is not possible to just model it like that and look at it visually to see if there's change in the data distribution. So we need some kind of algorithmic and statistical tools to detect that. And as the data changes, it might be that right now the model is making predictions on new regions in the data that it was not trained on, so it will not capture the patterns there, which might, of course, cause failure. So first and simplest way to solve it is just do few univariate statistical tests, something like Kolmogorov-Smirnov test or chi-square test or exact Fisher test. When we look at every single feature separately, we look at the distribution previously, either during training or maybe last month, last week, last day, and compare it to the current distribution. And if it is statistically different, it means that we do have data drift, and this data drift might be kind of a symptom of incoming model failure. If we want to look at it not from the perspective of just one variable at a time, but we want to look at them at the same time, a very nice way to do it is to just run anomaly detection. We fit our anomaly detection algorithm, something like one-class SVM or isolation forest. We run it on the data where we do have the labels and we know what is the performance. And then as the time passes, we will just see whether there's more and more anomalies coming. And if we see more anomalies in our current dataset compared to the previous dataset, it's a strong indication that data drift is happening. And again, that might cause problems. And the last most advanced way to detect data drift is using generative adversarial neural networks. When we train the GAN on our training data, so it learns how to parrot, how to mimic the training data, and then we use the discriminator part of the network in order to basically see if the new production data is significantly different from the training data. That way we can really capture all characteristics of the data set using a neural network. It's the most advanced way and should be the most robust and most efficient, but of course GANs are very hard to train and they tend to get stuck in local minima, so it's easier said than done. Now, I'm going to walk you through a mini example of how to do it just when you can, tomorrow start working again. And if you're curious about whether there's actually data drift currently in my model, what you can do is you import one of the statistical tests I mentioned. You could, for example, import Kolmogorov-Smirnov test to work on continuous data. you take one feature that you're interested in, you set the default p-value to 0.05, you run the test compare for a given feature, comparing the previous month distribution with the current month distribution. And if the result of the test is that the distributions are different with p-value below 0.05%, it means that the feature has drifted. Very simple thing, but just something for you to try out later on. If you want to work with categorical features, then you would need to use chi-square test. For binary categorical features, you should normally go for the Fisher's exact test. These are just names. They work in a reasonably similar way. To give you a quick overview of how the KS test works, it takes two distributions. It looks at the cumulative distribution, and then it basically computes the area between those two. And if it's sufficiently big, it tells you that there is drift in the data. So now let's move on to the second way of trying to detect whether the model has failed, and this is the concept drift. Concept drift can quickly be defined as change in the decision boundary. So again, we have a 2D example here, and on the training data, our decision boundary has been determined, or maybe it was real like that. And now if we had looked at the labels, we would actually see that the decision boundary looks like this. So it's completely different. But the patterns are different, the model doesn't work anymore. And that, of course, strongly implies that your model has failed and your predictions won't be as good as they used to be. How do we try to really detect concept drift? This is hard in itself. And if we have access to labels, we can do a few simple things. First one would be just to do the correlation analysis between inputs and the labels, not the outputs, but the labels themselves. And if we see that the correlations themselves are drifting, then it means that we have concept drift because the pattern between the inputs and the outputs has changed. Then another thing what we can do, a bit more advanced than just correlations, we can create a model, your normal XGBoost, let's say, fit it on the training data, then fit it again from scratch on last month, last week, last day, and then see if the model parameters are significantly different. If they are, again, we're just right now trying to see if the mapping between the pattern, between the inputs, the outputs has changed. If it had, then we have concept drift. And that is all nice, but we don't really need it that much if we have access to labels, because then we can just measure performance. So what can we do if there's no labels? So we don't have the ground truth, the actuals. And one thing we can do is we can measure the drift in the current feature importance. Imagine we have our XGBoost model, and the model has certain feature importance. Maybe the most important thing is the credit history, then it's the current income, and then maybe location. We take that and we look at the feature importance for every single example and then sum together using something like SHAP values in the training, and then we compare it in production. It might be that because of the data drift, actually the features that tend to be important for every single example in the production will be slightly different than the one in the training. And if we all sum them up together and average them, the feature importance is going to be different. And that kind of implies that there's still concept drift on top of just data drift. Now, moving on to the last part of detecting machine learning failure. Here we try to directly measure performance, or at least estimate it. And the easy thing we can do is to just measure and do statistics on the metrics, on things like F beta scores, F1 scores, precisions, RMSEs, etc. If they change, then of course our model is failing, as simple as that. And again, things get interesting if the labels are delayed or not available at all. Imagine that you're doing document classification. You will never really have access to labels because the machine is doing the job that the person was supposed to do. So right now you will never see the true label unless you actually have a human do the same work all over again, which defeats the purpose of using machine learning in the first place. So what we can do then is, instead of trying to see whether the model is correct or not on every single label, which basically is recreating the model, we can look at the aggregate performance which funnily enough is easier to do than just looking at every single example. I will not go into details now, but happy to answer questions later. Why is that? But we can estimate the aggregate performance using things like data drift, concept drift, the features itself, statistics. We put that all in the model, and another machine learning model built on top of our current machine learning use case that takes the input data from the past as inputs for machine learning, inputs and outputs from the past as inputs to the model. And then as outputs, we have the aggregate performance of the model, again, from the past on our historical data. And we build this model, we fit it, and then we can estimate the performance on current data set when we don't have the labels. It is not guaranteed to work. Our current version is just a prototype. It seems to be quite robust, but of course, it's an open question, and by some definitions, it's impossible to fully solve. And then the last thing, again, something easier, is to do statistics on business KPIs. If we have access to direct business KPIs, then of course we can just look at them and see how they change. Maybe it would be the volume of applications, etc., etc. And if it goes down, then it's a problem. So that was how to solve it from kind of algorithmic perspective. Now let's look at the architecture, the engineering perspective of that. What I have here is a very simple, radically simplified kind of diagram of how a typical machine learning system looks like. So on the left here, we have a business process, which emits some kind of data that is taken as a model input. So your typical features, right? Credit score, credit history, income, location, occupation, things like that, for example, with our running example of credit scoring. So this is the model input. Then we have a machine learning model that does its magic, and then it outputs model output, obviously. What we need to do is we take those two, then you take it into your machine learning model, machine learning monitoring system, whatever it is. You take those two things, you compute data drift, you compute concept drift, you try to estimate performance. And if we have also access to the database, to the downstream data, things like business KPIs, things like labels or ground truth, so whether the model has failed, whether the credits was successful with it based on has paid back the credit or not, and maybe some other data. If we can get access to that, we should also take it into account. And the last thing, if we do have access to the model itself, it will also allow us to directly see what are the assumptions that the model has, whether, for example, it's strictly linear model. Then if there's some new non-linear relationship in the data, we know for a fact, we don't need to check it, that the model is not capturing that, so there's a problem. If we don't have direct access to the model, we can still create a surrogate or fake or shadow model, which should quite well approximate the machine learning model that's there, but maybe the assumptions won't really be the same. Then we take it into our machine learning system, where we compute all these things, and then we can output it in a dashboard as notebook instance, just as an API, so that the downstream services, something like maybe retraining framework, can take it and act on the alerts. If there's an alert that the model performance is not good, and the reason for that is that the data has drifted, maybe just retraining will fix it. So we take that and then we use it later on. So that's basically it. What I wanted to share before we finish is just a few resources. There is a kind of decent-ish library called Scikit Multiflow, developed by guys from the data streaming community. It only works with data streaming, so it will not work out of the box on most machine learning use cases. But nice thing about it is that they do have a lot of drift detection algorithms. They're a bit more advanced than simple statistics. So yeah, you're welcome to give it a try. Few of our competitors, I'm just gonna go with the biggest ones. Fiddler AI, they're based in Silicon Valley, Arthur AI based in New York, enterprise stuff. And then when it comes to interesting things, a bit more self-promotion, I have a blog on how to get started with monitoring. Give it a read if you like it. And then a few papers, kind of seminal papers about how to do drift detection. Basically, these two guys are the biggest names when it comes to data drift detection. João Gama is Portuguese. Albert Buffet is from Paris, I think. So give it a go. You will see this presentation later. You can just click on the links. You don't have to like take screenshots, but you're welcome to. And last thing, more self-promotion is, we're looking to hire data scientists and also data engineers, but mostly data scientists currently. So come work with us. We are super cool people, very small startup, 4 people. We are VC funded, so we're not gonna run out of money anytime soon. We offer good salary, we offer stock options. We are fully remote. I live in Portugal. One of my co-founders right now is in Spain, another in Belgium. And yeah, we're cool people. Join us. Also, feel free to add me on LinkedIn, send me an email or anything like that. Also, if you need machine learning monitoring, also let me know.